The new sound card looked harmless enough. It was a narrow circuit board covered with chips, connectors, and a few tiny plastic jumpers that seemed almost too small to matter. For a PC owner in the early 1990s, installing it could begin with the kind of confidence the expanding computer industry encouraged. Shut down the machine, remove the beige metal cover, find an empty expansion slot, press the board into place, tighten a screw, reconnect the cables, and switch the computer back on. The expectation was simple. The PC would now have sound. Instead, the machine might start normally while the new card remained silent. A mouse that had worked minutes earlier could stop responding. A modem might vanish from the communications software that used it. A game could freeze when it tried to play digital audio. Nothing had necessarily broken. The sound card could be fully functional, and so could every device already inside the computer. The failure might come from something less visible. Two pieces of hardware could be trying to use the same limited internal resource. Fixing that problem could mean shutting the machine down again, reopening the case, finding the correct page in a manual, moving a jumper to another pair of pins, restarting, testing, and discovering that the change had created a different conflict somewhere else. What looked like a simple upgrade could become an evening spent negotiating with an architecture the customer had never intended to study. The roots of that problem reached back to one of the greatest strengths of the IBM compatible PC. From the beginning, expansion slots allowed owners and manufacturers to add capabilities that had not been built into the original machine. A basic computer could later gain better graphics, additional storage, communications hardware, networking specialized controllers, sound, or other functions. That flexibility helped create an enormous market for add-in boards, yet each new device needed a dependable way to communicate with the processor and the rest of the system. Hardware had to signal when it required attention. Software needed a known location through which it could exchange commands and data with a device. Certain peripherals needed efficient ways to move information without requiring the processor to supervise every transfer. These requirements produced terms that would become painfully familiar to many PC owners: IRQ, I/O address, and DMA channel. An interrupt request, usually shortened to IRQ, gave hardware a way to tell the processor that something needed to be handled. The concept itself was straightforward. The difficulty came from the fact that early PC designs did not provide an unlimited number of independent interrupt lines. Several were already committed to essential functions, leaving expansion devices to work within a restricted set of choices. I/O addresses created another form of territory. Software needed to know where a device could be reached. If incompatible hardware tried to occupy the same address range, the machine could behave unpredictably. DMA channels added another constraint for devices that moved substantial amounts of data. None of these mechanisms was a design mistake in isolation. They reflected the practical needs of the computers for which they had been created. The trouble was that the personal computer did not remain the machine its early designers had imagined. During the late 1980s and early 1990s, PCs accumulated new roles at remarkable speed. They became communications terminals, office network clients, gaming systems, multimedia machines, and platforms for increasingly specialized hardware. A modem might share the computer with a network adapter. A sound card could need an interrupt, one or more DMA channels, and a particular range of I/O addresses. A SCSI controller might connect disks or scanners. CD-ROM drives entered homes and offices as multimedia software spread. Each addition increased the usefulness of the machine while making its internal resource map harder to manage. The computer itself often lacked a universal way to examine every legacy expansion board, determine exactly what it was, learn every configuration it supported, and arrange those settings automatically. Much of that knowledge still had to come from the person installing the hardware. Manufacturers tried to make the process manageable. Manuals contained tables showing possible interrupts and addresses. Tiny jumper blocks allowed owners to select one configuration instead of another. Some cards used DIP switches. Others arrived with software utilities that changed settings electronically, reducing the need to touch the board itself. Those improvements did not remove the central difficulty. Someone still had to know what the rest of the machine was using. An experienced technician could often reconstruct the resource map from memory, documentation, and symptoms. A beginner faced instructions that might say, in effect, choose an unused IRQ without explaining how someone unfamiliar with the architecture was supposed to know which interrupt was actually free. A wrong choice did not always produce a clear error message. One device might stop working while another appeared normal. Software could complicate the situation further. A card physically configured for one address would remain invisible to an application looking somewhere else. Sound hardware became one of the most memorable examples because games frequently asked users to enter configuration values manually. Before hearing a single note, an owner might have to select an address, an IRQ, and a DMA channel from a setup screen. Those numbers were not academic details. One incorrect setting could produce silence, distorted audio, instability, or a program that refused to start. As more peripherals entered ordinary PCs, the number of possible interactions grew. A machine upgraded several times over a few years could become an accumulation of old decisions, each new card constrained by what earlier hardware had already claimed. The irony was that this difficulty existed because the PC's expansion model had succeeded so well. IBM-compatible computers offered owners an unusual degree of freedom. Hardware companies could build boards for countless purposes, and customers could keep modifying machines long after purchase. The same openness that encouraged innovation also meant that components from different manufacturers had to coexist inside an architecture with limited resources and no universal automatic referee. By the early 1990s, that tension was becoming harder to ignore because the identity of the PC customer was changing. Personal computers were moving rapidly beyond enthusiasts and technicians into schools, offices, and homes. Buyers wanted a modem because they wanted to communicate. They wanted a sound card because they wanted games and multimedia. They wanted networking because their work required it. They did not necessarily want to learn the electrical inheritance of the original IBM PC. Graphical interfaces were making software easier to approach at the same moment hardware installation could still require handwritten notes about interrupts and repeated trips inside the case. The contradiction was becoming obvious. A computer powerful enough to display sophisticated graphics and play digital audio could still depend on its owner to prevent two expansion boards from asking for the same resource. Manuals could improve, setup programs could become friendlier, and manufacturers could choose conventional defaults, but those measures treated symptoms rather than the underlying problem. As the number and variety of PC peripherals continued to grow, the configuration model itself had to change. The machine would need a way to learn what hardware had been installed, understand what that hardware required, and make choices that previously belonged to the person holding the screwdriver. Doing that would mean asking an old and immensely successful platform to behave in a way it had never originally been designed to behave. The idea of letting the computer configure its own hardware sounded far simpler than the engineering required to make it happen. Conventional ISA expansion boards did not necessarily possess a standardized method for announcing their identity, describing their resource requirements, offering alternative configurations, and accepting settings chosen by software. A card could occupy a slot and function perfectly once configured, yet reveal very little about itself to a system attempting to organize the machine automatically. Solving that problem without abandoning the enormous installed base of IBM-compatible hardware required a transition rather than a clean break. During the early 1990s, Microsoft and Intel became central participants in an effort to build that transition around a concept that would soon become one of the most recognizable phrases in personal computing: plug and play. The name described the experience the industry wanted customers to have, not the complexity hidden underneath it. A person would install a device, start the PC, and allow the machine to determine what it appeared, what resources the device required, which driver should control it, and how it could coexist with everything already present. For ISA hardware, the first obstacle was identity. Automatic configuration could go nowhere if the computer could not distinguish one expansion board from another. A plug-and-play capable ISA device therefore needed to expose standardized identifying information and describe the resources it could use. Instead of arriving with a single rigid configuration selected beforehand, a board might indicate that several interrupts were acceptable, more than one I/O range could work, or different DMA channels were available. That changed the logic of installation. Under the older model, the owner chose settings first, and the computer simply operated within those choices. Plug and play attempted to let the hardware present its possibilities and allow the system to select a workable combination. Multiple compatible cards complicated discovery because they had to be distinguished before ordinary operating resources had been assigned. The plug-and-play ISA design therefore included a method for isolating devices and addressing them individually during configuration. Once recognized, a card could expose the information needed for software to decide where it belonged. The important innovation was not the disappearance of IRQs, DMA channels, or I/O addresses. All of them remained relevant. What began to disappear was the assumption that a human being had to arrange them manually. A conflict that once sent someone searching through a manual could, under ideal conditions, be prevented by configuration software before the device entered normal operation. That ideal depended on more than the expansion card. Hardware needed to describe itself accurately. Firmware had to cooperate with the startup process. The operating system needed to maintain a useful picture of the machine and understand which resources were already occupied. Drivers had to correspond to the configuration that had actually been assigned. Plug and play was therefore not one chip, one Windows feature, or a single invention hidden inside a motherboard. It was an agreement among several layers of the PC. Weakness in any one of them could undermine the experience. This was especially important because the new system had to coexist with hardware that did not know the agreement existed. Millions of ISA cards had already been manufactured. Businesses relied on specialized controllers and network hardware. Home users owned modems, sound cards, and other devices they expected to carry forward when upgrading. Software had been written around conventional configurations. Backward compatibility was one of the IBM-compatible platform's greatest commercial strengths, and an automatic configuration system that worked only after users discarded all older equipment would have been of limited value. New plug-and-play devices could participate in discovery and negotiation. Legacy boards often could not. If an older card had been set manually to use a particular interrupt, the system needed some reliable way to know that the resource was already occupied. A silent device created a blind spot. Software might believe it had found a free assignment when the hardware itself told a different story. The industry was therefore building an automatic resource manager for machines in which some components could explain their needs and others could not speak at all. That problem shaped the transition. The goal was not merely to invent a better expansion card. The PC needed a more organized understanding of everything attached to it. Hardware identity could be associated with the software intended to control it. Resource requirements could become structured information rather than values printed only in a manual. Alternative configurations could be evaluated systematically instead of discovered through trial and error. The operating system could begin assuming responsibilities that earlier users had performed themselves. This change arrived at a moment when expectations surrounding personal computers were rising quickly. Graphical operating systems encouraged the belief that machines should be understandable without specialized training. Multimedia was becoming a major selling point. Offices expected networks and communications hardware to function across large fleets of PCs. Hardware installation was no longer a niche concern for enthusiasts. It had become part of the mainstream customer experience. A peripheral manufacturer could build an impressive product, yet lose customers if installing it required a lesson in interrupt assignments. Ease of configuration had become an industry problem. Plug and Play offered a way to address that problem without abandoning the openness that had made the PC ecosystem valuable. It also represented a deeper shift in the relationship between software and hardware. Earlier computers frequently required owners to understand internal constraints because the machine had no other source for that knowledge. The new model expected the components themselves to provide information. The computer would assemble that information, compare competing requirements, and make decisions beneath the interface. Configuration would continue to occur, but fewer of its details would have to reach the person using the machine. On a clean system containing compatible hardware, the promise was convincing. Install a new board, start the computer, allow it to identify itself, choose resources, associate a driver, and become available with minimal intervention. The process seemed capable of turning one of the most frustrating parts of PC ownership into an ordinary background task. The difficulty was that real computers were rarely clean systems assembled entirely from hardware designed around the newest specification. They were machines accumulated over time, filled with old boards, newer boards, varying BIOS implementations, drivers from different manufacturers, and settings inherited from previous upgrades. Automatic configuration was about to leave the controlled language of engineering documents and enter millions of unpredictable desktops. That was where the difference between designing plug and play and living with plug and play would become impossible to ignore. By the middle of the 1990s, automatic hardware configuration was moving from specification into everyday computing. Windows 95 arrived in a market where PCs were rapidly becoming multimedia and communications machines. CD-ROM software was spreading, sound hardware was increasingly expected, modems connected homes to online services, and network adapters were common in offices. The operating system approached hardware installation with far greater ambition than many users had experienced before. It attempted to identify devices, connect them with appropriate drivers, and coordinate the resources required to make them function. For someone accustomed to setting jumpers by hand, seeing Windows announce that it had detected new hardware could feel like a glimpse of a different future. When the pieces cooperated, the improvement was substantial. A compatible card could be installed, recognized during startup, assigned suitable resources, and prepared for use without forcing the owner to decide every technical detail. Device Manager provided a centralized view of installed hardware and gave users a place to investigate trouble that previously might have required several unrelated utilities. The computer seemed to possess a growing awareness of what existed inside it. Yet Windows 95 did not enter pristine machines built entirely around the newest assumptions. It entered PCs that reflected years of technological accumulation. One system might contain a recent plug-and-play sound card beside a manually configured modem. Another might carry an older network adapter installed by an office technician, a SCSI controller supporting expensive equipment, and a BIOS designed before automatic configuration had become central to PC architecture. Every part could work correctly on its own. Together, they created exactly the environment that made the new model difficult. A plug-and-play device could report the resources it was capable of using. A legacy ISA board might remain silent. If that older hardware had been set to a particular interrupt or I/O address and the operating system did not possess an accurate record of the choice, a resource that appeared free in software might already be occupied electrically. The automatic system could make a rational decision based on incomplete information and still produce a conflict. The result was not evidence that the underlying idea was meaningless. It revealed the cost of introducing negotiation into an ecosystem that had spent years operating without it. Drivers created another layer of uncertainty. Recognizing a device did not guarantee that the software controlling it would behave correctly. Manufacturers were adapting products to a rapidly changing Windows environment, and quality varied. The correct driver might not be available on the installation media. A newer version could be required. Software might mishandle resources or assume behavior the hardware did not provide. The customer could watch Windows detect a card successfully and still end up with a device that refused to function. Troubleshooting had moved, but it had not vanished. Instead of immediately reaching for a jumper, the user might open Device Manager and find a warning symbol beside the troubled component. Resolving the problem could involve reinstalling a driver, changing a setting, disabling unused hardware, reserving a resource for a legacy device, adjusting BIOS options, or eventually reopening the case and returning to manual configuration. For experienced owners, such work remained familiar territory. For newcomers attracted by the promise of effortless setup, it could be bewildering. The sarcastic nickname plug and pray captured this gap between expectation and experience. It lasted because the technology was successful enough to make people believe installation should be automatic, yet incomplete enough that failures remained common and memorable. Treating that phrase as proof that plug and play simply failed misses what was happening. Many installations genuinely became easier. More devices could be detected without manual intervention. Hardware identity and driver selection were becoming connected in useful ways. The system was taking over decisions that once belonged entirely to the person building or upgrading the machine. The frustration came from trying to introduce those improvements while preserving backward compatibility with years of hardware that followed different rules. The IBM-compatible ecosystem had grown powerful, partly because customers could keep equipment across upgrades. Businesses were not eager to discard specialized boards simply because a new configuration standard had appeared. Home users expected existing modems, sound cards, and controllers to remain useful. Manufacturers wanted access to the enormous installed base. Compatibility therefore prevented the industry from starting over, and every preserved legacy device carried some part of the old configuration model into the new era. Firmware differences added another complication. BIOS implementations varied among motherboard and system manufacturers, and the division of responsibility between firmware and the operating system was not always obvious to the user. Certain machines exposed setup options affecting resource allocation. Advice for resolving a problem could lead from a Windows control panel into BIOS screens filled with unfamiliar settings. The attempt to hide hardware complexity had created a chain of cooperating layers, yet when those layers disagreed, diagnosing the failure could be more difficult than changing a single jumper. Multimedia systems placed especially heavy pressure on this transitional architecture. Sound cards, modems, network adapters, storage controllers, game ports, and other devices could all demand resources from a finite pool. Automatic configuration could search for better arrangements, but software could not create additional capacity where the underlying design offered none. Plug and play was a resource allocator, not a source of unlimited resources. This distinction mattered because the consumer promise was much simpler than the engineering reality. The name suggested an action with only 2 steps: connect the device, then use it. Beneath that experience were hardware identification, firmware behavior, driver compatibility, resource availability, and the compromises required to keep older devices alive. Those details rarely appeared in marketing because the entire purpose of the technology was to make them unnecessary for the customer. When the process failed, however, all of that hidden complexity surfaced at once. The solution was not to abandon automatic configuration and return permanently to handset hardware. The difficulties instead demonstrated that the deepest limitations were architectural. ISA had been created under assumptions that predated the idea of a consumer PC automatically discovering and organizing a diverse collection of peripherals. Plug and play could extend the bus and reduce its problems, but there was a limit to how elegantly new behavior could be grafted onto an old foundation. Meanwhile, PCI was spreading through new machines. It had been designed with software configuration and systematic device discovery much more firmly in mind. The contrast became increasingly important. On legacy ISA, automation often had to infer, reserve, or negotiate around the past. On newer buses, structured configuration could be part of the normal relationship between the device and the system. As more hardware migrated toward PCI, the resource problem began to change character. Interrupts still existed, addresses still had to be assigned, and drivers remained essential. But the person sitting at the keyboard was becoming less responsible for determining where every device belonged. The turbulent years of early plug-and-play had exposed something the industry could no longer avoid. Making hardware installation truly automatic would require more than improving Windows setup screens. The architecture of the PC itself had to evolve so that software could understand the machine without first asking the owner to explain it. PCI provided one of the clearest signs that this evolution was taking place. Instead of treating automatic configuration as an addition to a legacy expansion environment, the bus incorporated a more systematic way for software to discover devices and determine what they required. Standardized configuration information allowed the platform to identify hardware and assign resources without depending on the owner to decode jumper tables. The electrical and software details remained complicated, but they were increasingly designed for machines to manage rather than people. That distinction changed the experience of expansion. On an ISA system, installing a board could begin with a human choice about interrupts or addresses. On PCI, the expectation shifted toward enumeration and software-controlled assignment. The transition was gradual. For years, motherboards carried both ISA and PCI slots because the industry could not abandon existing hardware overnight. Mixed systems preserved some of the old difficulties, but every new device built around automatic discovery reduced the number of silent components the operating system had to accommodate. Network adapters, storage controllers, sound hardware, and other peripherals increasingly moved into an environment where configuration data could be read directly rather than reconstructed from assumptions. Windows evolved alongside the hardware. Resource management became an ordinary operating system responsibility. The system could compare the requirements of different devices, determine which assignments were available, and arbitrate among alternatives when more than one configuration was possible. The practical consequence was simple even when the mechanism was not. Decisions that once required opening the case were increasingly made before the desktop appeared. Interrupt handling also became more flexible as PC architecture moved beyond the constraints inherited from the earliest IBM-compatible machines. The old image of every expansion device fighting for exclusive possession of one precious IRQ gradually became less useful. Appropriate hardware and operating systems could support more sophisticated interrupt routing and sharing. The numbers still existed beneath the surface, but their relationship to installation was changing. A user no longer had to think about every interrupt as a physical claim that must be protected manually. Another shift concerned the boundary between firmware and the operating system. As PCs became more complex, the older division of responsibility between BIOS routines and system software became increasingly awkward. The industry needed a more standardized method for describing platform hardware, power states, and configuration information. ACPI emerged in the mid-1990s as part of that broader change. Although it became widely associated with power management, its importance was not limited to making computers sleep or wake. ACPI helped establish a model in which firmware could provide structured descriptions of the platform while the operating system assumed greater authority over configuration and power decisions. It should not be understood as a renamed version of plug and play. The two address different layers of the system. Their historical connection lies in the direction of travel. Both reflected a PC industry moving away from isolated conventions and toward architectures in which software received better information about the hardware it was expected to manage. Early implementations could still be imperfect. Firmware bugs remained capable of creating strange behavior. Drivers could fail. Motherboards differed in quality, and an operating system upgrade could expose assumptions hidden in older components. Yet those failures no longer changed the larger trajectory. The operating system was becoming the central organizer of an increasingly self-describing machine. Hardware identity, resource assignment, driver association, power management, and device state were moving into a coordinated software model. As that transition continued, another standard made the new philosophy visible, without requiring users to understand any of the architecture beneath it. USB turned peripheral installation into an external dynamic event. Connecting a compatible device did not require shutting down the computer, removing its cover, choosing an expansion slot, or touching a jumper. The host could detect that a device had appeared, retrieve identifying information, establish communication, and connect it with the software needed to control it. This model did not become universal overnight, and early USB support passed through its own period of incomplete hardware and software compatibility. By the Windows 98 era, however, the idea of attaching many kinds of peripherals and expecting automatic detection was becoming increasingly familiar. That experience represented a major departure from the expansion rituals of only a few years earlier. The user no longer had to configure internal electrical resources because the interface had been designed around enumeration and software management from the start. A mouse, keyboard, printer, scanner, game controller, storage device, or other peripheral could appear as something the operating system was expected to recognize. Failures still occurred, but the expectation had reversed. In the ISA era, troubleshooting was an accepted part of installation. In the newer model, automatic recognition was the normal case, and manual intervention increasingly felt like evidence that something had gone wrong. Driver installation followed the same direction. The software controlling a device remained essential, yet hardware identity could now be connected more systematically with the correct driver. Instead of relying entirely on the owner to know which files corresponded to which board, the operating system could use the device's reported identity as part of the installation process. Device Manager became a visible expression of the underlying organization. A user could inspect hardware status from one place, while the resource allocations and relationships that made the machine function were handled largely beneath the interface. None of these developments erased the engineering problems that plug and play had confronted. They changed the environment in which those problems existed. Scarce legacy resources mattered less as older buses disappeared. More capable interrupt systems reduced dependence on the simple conventions of early PCs. Firmware and operating systems gained better ways to exchange configuration information. New peripheral interfaces were created around automatic discovery, rather than adapted to it after the fact. By the end of the 1990s, the industry was no longer trying merely to make ISA configuration less painful. It was replacing the assumptions that had made manual configuration normal. A generation earlier, the owner had often served as the final authority on what hardware occupied which resource. Now that authority increasingly belonged to the system itself. The change was not complete, and it was not the work of a single technology. Yet it had progressed far enough that the knowledge once required to install a PC peripheral was beginning to lose its everyday value. The final consequence of that transition would be measured not by another specification or another bus, but by what computer users eventually stopped needing to know. That disappearance of knowledge was easy to miss because it happened gradually. There was no single day when PC owners stopped thinking about IRQs. No announcement declared that DMA channels had ceased to matter. The underlying mechanisms continued to exist and evolve, but they became less visible as hardware, firmware, and operating systems assumed more of the work required to coordinate them. A person who had upgraded PCs in the early 1990s might remember interrupt numbers almost instinctively. Someone who began using computers a decade later could spend years installing peripherals without ever needing to learn why those numbers had once mattered. That contrast captures the historical importance of the transition better than any marketing slogan. The personal computer did not become less complicated. In many ways, it became vastly more complex. What changed was how much of that complexity the user was expected to manage directly. Device Manager illustrated the new relationship. Hardware could still be inspected, drivers could still fail, resources could still be examined when troubleshooting demanded it. Yet these details had become diagnostic information rather than prerequisites for ordinary installation. Most users did not need to plan the machine's internal resource map before connecting something new. The system maintained that knowledge for them. This shift extended well beyond desktop expansion cards. PCI Express continued the movement towards software discoverable internal hardware. USB made automatic external device recognition routine. Laptops integrated components that ordinary owners could not realistically configure by hand even if they wanted to. Docking systems, removable storage, cameras, webcams, wireless adapters, input devices, and later generations of peripherals inherited the assumption that the machine should detect change and respond without requiring the user to understand the mechanisms underneath. That expectation became so strong that automatic configuration disappeared as a selling point. It turned into basic behavior. When a modern peripheral fails to appear, the experience feels abnormal precisely because decades of engineering have trained users to expect recognition as the default. Plug and play did not create that world by itself. Its historical significance lies partly in showing what had to change before such a world could become dependable. Early automatic configuration exposed weaknesses that a cleaner narrative might hide. Legacy devices that could not identify themselves revealed the value of standardized discovery. Inflexible resource assignments demonstrated the cost of preserving architectural assumptions from the first generations of PCs. BIOS inconsistencies showed that firmware and operating systems needed a clearer relationship. Driver failures proved that detecting hardware was not enough. The machine also needed a reliable software path for controlling what it had found. Later technologies addressed these problems at different layers rather than through one universal cure. This is why describing plug and play as the invention that ended IRQ conflicts would simplify the history too far. IRQ conflicts faded from everyday PC ownership because the entire environment changed around them. New buses were designed for software-controlled configuration. Resource management became more sophisticated. Interrupt architecture grew more flexible. Firmware communicated more structured information. Driver models improved. External interfaces, such as USB, were built around automatic discovery. The old ISA world was not perfected into modern computing. It was gradually displaced. Plug and play belongs at the center of that transition because it attempted to shift responsibility at a moment when the old assumptions were still everywhere. Its failures were therefore unusually visible. The technology asked legacy PCs to behave like systems that had not yet been fully built. In doing so, it helped establish an expectation that would outlive the ISA hardware for which some of its most difficult work had been designed. The consequences were practical as well as technical. Easier installation widened the market for peripherals. A customer no longer needed to be comfortable opening a case and interpreting resource tables before considering an upgrade. Businesses could deploy hardware with less machine-by-machine tuning. Manufacturers had stronger reasons to provide devices that identified themselves predictably and drivers that integrated cleanly with the operating system. As automatic configuration became normal, responsibility shifted toward the companies building the hardware and software. A peripheral that demanded obscure manual settings increasingly looked unfinished rather than merely technical. That reversal changed the culture of PC ownership. Earlier machines often exposed their limitations directly to the person using them. The owner learned those limitations because the computer required assistance. A modem might claim one interrupt, a sound card another, and a controller a third. Installing hardware meant understanding enough of the machine's internal organization to avoid collisions. Later systems still had constraints, but the architecture increasingly mediated them. The user interacted with the device, while the operating system dealt with identities, drivers, resources, and routing beneath the visible interface. Ease of use emerged not from abolishing technical complexity, but from deciding where that complexity should live. This is why the sound card from the beginning of the story now feels so distant. Picture the open beige tower again. The board has been pressed into an ISA slot. A printed manual lies beside the keyboard. Somewhere on the card, a jumper determines which interrupt it will request. The owner has to know enough about every other device in the machine to decide whether that choice is safe. If the wrong two components collide, the computer may offer little explanation. The person troubleshooting the failure has to reconstruct the invisible conflict from symptoms. At the time, nothing about this seemed extraordinary. It was simply part of owning an expandable PC. Then, piece by piece, that responsibility moved elsewhere. Hardware learned to identify itself. Buses were redesigned around software configuration. Operating systems became resource managers. Firmware exposed more useful information. Drivers became connected to reported device identities. Interfaces, such as USB, made detection part of the basic act of connecting a peripheral. The old rituals did not disappear because interrupts stopped existing or because computers no longer needed configuration. They disappeared because the machine became capable of performing more of that configuration without involving the person using it. Plug and play arrived during the awkward middle of that transformation, when the industry wanted automatic behavior but still had to support hardware built for manual control. That is why its history contains both genuine breakthroughs and memorable frustration. It did not sweep away IRQ conflicts in one clean victory. It helped move personal computing toward an architecture in which those conflicts no longer belonged to ordinary users. The real achievement was never that configuration stopped happening. It was that, for most people, it finally stopped feeling like their job